Today I am going to explain the data science assignment. So first question is explain the difference between supervised and unsupervised learning. Provide examples of the algorithms for each type of learning and discuss scenario where each would be appropriately used. So supervised learning will take the example as the teacher. This is where we give the machine algorithm for a bunch of data that is already labeled with the correct answers. The algorithm's job is to learn the rules that connects the question to the answers. So example would be spam filter for your email. We feed the algorithm thousands of emails. Each email is labeled as either spam or not spam. The algorithm then learns the pattern. It learns that emails with words like congratulations you won or free are often spam. The goal is for it to get so good at learning these patterns that when a new unseen email arrives, it can accurately predict or classify if it is spam or not spam. Supervised learning is used when you have a specific target you want to predict. Algorithms for classification like our spam filter. Common algorithms are logistic regression and decision tree. Algorithm for regressions, which is predicting a number, not a category, like what will this house price be. You would use linear regression. Scenarios you would use this to predict house prices, identify tumors in medical images labeled as tumor and not tumor, or forecast sales for next month. Summary. Supervised learning uses labeled data to make prediction. Now we have unsupervised learning. In this, we give the algorithm a bunch of data that has no labels. The algorithm job is to just explore this data and find any hidden patterns or structures all on its own. Examples: movie recommendation system. Imagine a service like Netflix has data of thousands of users and all the movies they have watched. There are no right answers here. It's just a raw data. They can use an unsupervised algorithm to group users based on their viewing habits. The algorithm might discover a group of people who love action comedies, another group that loves documentaries, and a third group that only watches 90s horror movies. The algorithm created these groups or clusters all by itself. Scenario: now when you watch a 90s horror movie, the system can see you belong to that cluster and recommend other movies that people in your group also loved. Unsupervised learning is used when your goal is discovery, not prediction. Algorithm. The most common type is clustering, and a famous algorithm is K-means clustering, which is exactly what our movie example just did. Scenario: you did also use this to segment customers into different marketing groups or to find abnormal data points. This is called anomaly detection. Now, to describe the concept of hypothesis space in machine learning, explain the algorithm find S find a hypothesis by find S for the following instances in a training set. We have origin like Japan, USA and Japan. Manufacturers like Honda, Toyota and Chrysler. And now color blue, green, blue, red and white. Decade 1980, 1970, 1990, 1980, 1980. Now type would be economy, sports, class would be positive, negative. Hypothesis space H. The hypothesis space is the set of all possible hypothesis rules that a machine learning algorithm can potentially learn. It's the search space or library of rules the algorithm is allowed to look through, find the best one. Now algorithm find S, the S is in find S is stands for specific. Its goal is to find the most specific rule or hypothesis that can correctly fit all the positive example in our data. Step is to start with the most specific hypothesis as 0 often by taking the attribute of the first positive example. For each new training example, if the example is negative, ignore it. If the example is positive and H does not cover it, generalize H by replacing any attribute that doesn't match with A. Wildcard. Now we have find as algorithm example. Find as algorithm example of training set tracing the hypothesis H at 0 start. Example 1 positive है. So it would be initialize H with the first positive example H1. Example 2 negative. Find S ignores a negative example H2. Example 3 positive. Compares H2 with Japan Toyota Blue 1990 economy. Japan is equals to Japan, keep Japan. Honda is equals to Toyota, generalized to question mark. Blue is equals to blue, keep blue. 1980 is not equals to 1990, generalized to question mark. Economy is equals to economy, keep economy. S3 is equals to Japan, question mark, blue, question mark, economy. Example 4 negative. Find as ignores negative example H4. Now we have example positive. Compare H4 with Japan, Honda, white and 1980 economy. We'll find the positive of it. Now final hypothesis H final is equals to Japan, question mark, question mark, question mark, economy. Now explain the purpose of training, test and validation sets in machine learning. What is cross validation and how does it differ from a simple training validation test split? Overfitting is when your model doesn't learn the general pattern, it just memorizes the exact answers from the data it trained on. A memorizing model is useless because it will be totally wrong when it sees new data in the real world. The simple split, we split our data into 3 separate sets. The easiest way to understand these 3 sets is with a school analogy. Homework, a quiz and a final exam. The training set, this is the biggest chunk of your data, maybe 70%. This is the practice homework. The model gets to see this data, learn the patterns and find the answers. The validation set, this is the smaller piece, maybe 15%. This is the midterm quiz. The model doesn't train on this after we do our homework training. We take the quiz validation to see how we did. Based on our quiz score, we might go back and change how we study, maybe try a different technique. In machine learning, this is called tuning or R model. The test set, this is the final 15%. This is final exam. It's been locked in a drawer the whole time. Only after all our studying and all our quizzes are completely finished, so we take the final exam. This one scores tell us final unbiased grade, how our model will actually perform on brand new data. Now we have problem with this simple split. Problem with this simple split is the main problem is that you might get lucky or unlucky with your split. What if just by pure chance all the easy problems ended up on your final exam? You did get a great score but it wouldn't be accurate. This is a big problem, especially if you have a small data set. You can't afford to just look away 30% of your data for a validation and testing. The solution to this is k-fold cross validation. Here's our 5-fold cross validation box. First, you still lock away your final exam test set. We never touch that. Then you take the rest of your data, your homework and quiz data, and split it into 5 equal chunks or folds. Now you run 5 experiments or rounds. Round 1 is you train on the first 4 folds and validate on the 5th fold. You write down the score. Round 2 you train on folds 1, 2, 3 and 5 and validate on the 4th fold. Write down the score. You keep doing this until every single fold had a turn to be the quiz set. With a simple split, you get the one quiz score. It might be a lucky score, it might be unlucky score. With five-fold score validation, you get five quizzes score. You then average them together to get a much more stable, reliable, and trustworthy estimate of how good your model really is. You are using your data more efficiently and you are protecting yourself from a single unlucky split. Key difference: a simple split uses a static chunk of data for validation. It's one experiment. Cross validation cleverly reuses the data, giving every data point a chance to be a validation set. Now we have sets. It's like running k experiments and averaging the results for a much more trustworthy score. Given the confusion matrix, find classification, accuracy, precision, recall, type 1 error, type 2 error, F1 score, sensitivity, specificity. Explain the importance of precision recall as compared to accuracy with an example. This box plot called as confusion matrix, and it's not as confusing as it looks. It just shows us where our model was right, where it was wrong. Actual is what was true. Predicted is what our model guessed. Let's find our four key values from the chart. Now, true positive, the model guessed positive and it was positive, that's 6. False negative, the model guessed negative but it was actually positive, that's a miss, that's 4. This is our type 2 error. False positive, the model guessed positive but it was actually negative, that's a false alarm, that's 2. This is our type 1 error. True negative, the model guessed negative and it was negative, that's 8. Now we can just plug these numbers into formulas. The calculation, classification, accuracy, what fraction of predictions were correct. Formula is TP plus TN upon my total. So calculated would be 0.70 or 70%. Precision, of all the times we predicted positive, how often were we correct? Formula TP upon my TP plus FP. So calculation would be 0.75 or 75%. Recall, also called sensitivity of all the actual positive cases, how many did we catch? Recall, also called sensitivity of all the actual positive cases, how did we catch? So formula would be TP upon TP plus Fn. Calculation would be 0.60 or 60%. Type 1 error, a false positive, count FP is equals to 2, rate so would be 0.20. Type 2 error, a false negative, count Fn is equals to 4, so rate would be 0.40. F1 scores a harmonic mean, a balanced average of precision and recall. Formula would be 2 into precision into recall upon precision plus recall. Calculation would be 0.667 or we can say 66.7%. Sensitivity same as recall. Calculation 0.60 or 60%. Specificity, all of all the actual negative cases, how many did we correctly identify? Normal formula would be Tn upon my Tn plus Fp. Calculation 0.80 or 80%. Now precision versus recall. Accuracy can be misleading, especially with imbalanced data, that is 99% of emails are not spam. Prioritize precision when false positive are very bad. Example, email spam filter. The cost of false positive is a good email, actual negative going to the spam folder, predicted positive. This is terrible. You could miss a job offer. The goal is to we want to be very precise when we predict on an email. If it is a spam, we want to be very sure if it's a spam. We rather let a few spam emails false negative get to the inbox. Now prioritize recall when false negatives are very bad. Example, medical screening for a serious disease. The cost of false negative is a sick person. Actual positive being told they are healthy. Predictive negative. This is catastrophic. The goal is to we want to catch all cases, we want to recall every single positive case. We'd rather have some false positive telling a healthy person to get the more test than miss a single sick patient. Discuss the importance of dimensionality reduction in machine learning. Compare and contrast feature extraction and feature selection as two approaches to dimensionality reduction and provide examples of techniques used for each approach. The important is dimensionality reduction in machine learning. Dimensions are just features columns in our data set like age, price, height, and so on. You might think that having more data and more features is always better, but that's not true. This is called the curse of dimensionality. Slower training, more features is equals to more data to process is equals to much slower and model training. Overfitting with too many features, a model can start memorizing the training data. Overfitting instead of learning the general patterns. Now, data sparsity is as a dimensional increase, the data points become very far apart from each other, making it difficult to find meaningful patterns. The goal is to reduce the number of features dimensions to make the model faster, simple, prevents overfitting, often more accurate by removing noise. Two approaches, selection and extraction, are comparison of the two main techniques for dimensionality reduction. We have features, what is it, analogy, interpretability, information loss, feature selection, feature extraction. So example techniques: feature selection, choosing filter method, that is chi-squared test correlation, uses static to rank features before training fast. Wrapper methods, that is recursive feature elimination, uses the model itself to wrap and test which subset of feature give the best performance. Slow but effective. Feature extraction, combining PCA, principal component analysis, the most popular method. It finds new access principal component that capture the maximum amount of variance information from the original data. LDA, linear discriminant analysis, similar to PCA, but it finds new features that maximizes the separation between the classes, good for classification. Now we have to define overfitting and underfitting in the context of machine learning models. Describe how these issues can be identified and list strategies to prevent or mitigate them. Underfitting, this is when model is too simple. It's like using a straight line to try and describe a complex curve. It fails to learn the basic pattern in the data. This is model with basic high bias. Overfitting, this is when your model is too complex. It doesn't just learn the main pattern, the signal, it also memorizes all the random noise in the training data. This is a model with high variance. Example, imagine you are a student, and an underfit student is one who did not study at all. They foil the homework, the training set, and they fail the final exam, the test set. An overfit student is one who memorized the answer to the homework. They get 100% of the homework, but the moment they see a new question on the final exam, they have no idea what to do and they fail. A good fit student is one who learned the concept. They do all well on the homework and can also apply the concepts to new problems on the final exam. That's our goal. Identification, we look to the gap between our training score and test score. Underfitting, if your model performance is poorly on the training set and poorly on the test set, your accuracy is low everywhere. The model is just bad. Overfitting, if your model performs great on the training set, like 99% accuracy, but poorly on the test set, like 60% accuracy. This big gap is the classic red flag. It's the student who memorize homework, they can't generalized to the final exam. Now mitigation. Once you have diagnosed the problem, you can apply the cure. To fix underfitting, your model is too simple. The answer is increase complexity. You can try a more powerful algorithm, or you can add more features for it to learn from. To fix overfitting, your model is too complex. You need it to simplify. So first is to the number one best cure in the world is get more data. It's much harder for a model to memorize 10 million example than it is to memorize 100. But if you can't get more data, you can use a simpler model, or you can use powerful techniques like regularization, which is way too penalize the model for being too complex. Another popular method is early stopping. You watch the model train, and as soon as it scores the validation set starts to get worse, you just stop the training before it gets a chance to start overfitting. Differentiate logistic regression and linear regression on the basis of hypothesis, parameters, and cost function. How gradient descent algorithm is used to optimize the parameter. Now we have the core difference, which is linear regression. Solves a linear regression form is to predict a continuous value, that is price, temperature, score. Example, how much will this house cost us? to to $250,000 or $3 lakh, etc. Logistic regression solves a classification problem. Goal is to predict the probability of a discrete class, that is yes or no, 0, 1, spam or not spam. Example, will this customer buy the product? Example, that is 75% chance of yes. Comparison on the basis of hypothesis. The model's equation for a linear regression, the hypothesis is a simple straight line. The formula is just y is equals to mx plus b. As the input x goes up, the input y goes up for or down forever. For logistic regression, the hypothesis is a S-shaped curve called a sigmoid. It takes this y is equals to mx plus b line but squeezes the output so it's always between 0 and 1. This is perfect because that's exactly what a probability is. Two parameters, the value 0. The parameters are just the numbers that model has to learn, the m and b. In linear regression, the parameters define the slope and intercept of the best fit line. In logistic regression, the parameters define the decision boundary, that's the tipping point where the S-curve crosses the 50% of marks, separating yes from no. Cost function, the error report. Cost function is how we tell the model how wrong it is. The goal is to get the lowest cost. For linear regression, we use mean squared error, MSE. It's simple. It measures the distance from each point to our line, squares it, and finds the average. If it's an error, you can measure in dollars or feet. For logistic regression, we use log loss. It's a bit more complex, but it's brilliant. It gives a huge penalty to the model if it's confident and wrong. For example, if the actual answer is yes and the model confidently predicts 0.1, it gets a massive error score. This forces the model to be a good probability estimator. How gradient descent optimization parameters. Goal is to find the best parameters theta that minimizes the cost function j theta. Analogy, a hiker trying to get to the bottom of a foggy valley. Begin with random values for parameters theta. The hiker is on a random part of the hillside. Calculation gradient, compute the gradient, the slope or derivative, or the cost function j theta at the current position. The hiker feels the slope of the ground under their feet to see which way is downhill. Take a step, update the parameter theta by taking a small step in the opposite direction of the gradient, that is downhill. The step size is controlled by the learning rate phi alpha, or we can update rule theta is equals to theta minus alpha and value. Repeat, go back to step 2 and keep taking small downhill steps. stop. When the gradient is 0, the ground is flat, you have reached the bottom, the cost is minimized, and the parameter theta are optimized. Now write a program in Python to implement logistic regression and linear regression for every method. Compute and display the implemented models evaluation measures whichever is applicable, such as accuracy and other values of different evaluation metrics such as confusion matrix, accuracy and recall and specialty and loss function, Ramsey and R2 score. Import organism, import NUPSE and NP, import pandas as PD. We have the code to find the confusion matrix, accuracy score, precision score, recall score, and F1 score. Now we'll make the function of it and we'll write full code of it. You can see in this PDF. Now we have write one hot encoding for the given data. Concept is machine learning models only understand numbers, not text categories like apple or mango. One hot encoding is a technique to convert these categorical features into a numerical format that the model can understand. The problem with label encoding, the value of fruit column apple is equals to 1, mango is equals to 2, orange is equals to 3 is an example of label encoding. This is often bad because it creates a fake order. It implies that orange 3 is greater than mango 2, which doesn't make sense. The solution: one hot encoding. We create new binary 0 or 1 columns for each unique category in the fruit column. One hot encoding data. Instead of having one fruit column, we are going to delete that column and create new column for each unique fruit. So we will get a fruit apple column, a fruit mango column, a fruit orange column. Then for each row we put a 1 in the column that matches that fruit and zeros in all the other new columns. So explanation would be the first row was apple, so our new table gets 1 under fruit apple and 0 for mango and orange. The scored row was second row was mango, so it gets a 1 under fruit mango and 0 for apple and orange. And third row was apple again, so it also gets a 1 under fruit apple. And the last row orange gets a 1 under fruit orange. Now, why KNN is considered as lazy learning. Discuss K nearest neighbor. Consider the following table. It consists of the height, age and weight. Target value for 10 people. The weight of value ID 11 is missing. Predict the weight of this person ID 11 based on their height and age. KNN is called a lazy algorithm or instance-based learner because it does no learning during the training phase. Training phase lazy because it simply memorizes and stores the entire data set. There is no calculation and no model is built. Prediction phase hard work. All the real work happens when you ask for a prediction. The algorithm must calculate the distance from the new point to every single point in the stored data. This is the opposite for an eager learner like linear regression, which works hard during training to find a formula. The best fit line: eager learners have a slow training phase but a very fast prediction phase. Discussion: K nearest neighbors makes prediction based on the K most similar data points, the neighbors from the training set. Now choose a K value the user and must choose a value for K, that is K is equals to 3 or K is equals to 5. Find neighbor, calculate the distance, that is Euclidean distance from the new unknown point to all the points in the training set. Make a prediction for classification. The predicts Prediction is the majority vote of the neighbors classes. If k is equals to 5 and 3, neighbors are pass, predicts pass. For regression, the prediction is average of the neighbor values. This is what problem requires. Now predict the weight for ID 11. New point, height is equals to 5.5, age equals to 13, weight is not known. So task is to predict weight regression. Step 1, choose k, will choose k is equals to 3. Now calculate Euclidean distance from ID 11, 5.5, 38 to all other 10 points. By putting the values in the distance formula, we'll find it. Now step 3, find the 3 nearest neighbors, smallest distance. ID 6 is equals to distance is equals to 2.2, weight is equals to 60. ID 5 distance is equals to 2.12, weight is equals to 72. ID 4 distance is equals to 4.202, weight is equals to 59. Fourth step is to predict the weight by averaging the neighbors' weights. Prediction would be 63.67. Final answer, the predicted weight for ID 11 is 63.67. That is the R and SIM semester paper of data science. Thank you.